Okay, the three topics that we are going to be looking at today, rectangular approximation methods, hence that geometric foundation in that paragraph is right. Okay, so RAM. Now, if you're a computer guy like me, RAM means random access memory, and you're like, I don't get it. But it actually, in math, in calculus, is a rectangular approximation method. Okay? Now, there's an LRAM, an RRAM, and an MRAM. Guess what LRAM stands for? Left. RAM. Left. RAM. There is a method we use that we use it unless I VOC. RRAM. Oh, rectangular. No, it's right. Yes, it means right. Any guesses on M? Midpoints, which is like the middle. You think of it as the middle. I don't know what's good. So RAM is used to define the area under the curve, which lies so beautifully from derivatives to integrals, from differential calculus to integral calculus. And boy, we are going to start taking a journey, children. Not the type of journey where like someone says getting a van and offer candy journey. A nicer journey. Well, no, for some of you, you calculus the same way as being beat up. So, anyways, consider an object moving at a constant rate of 3 feet per second. 3 feet per second. Okay? We have an object moving at a constant rate of 3 feet per second. Since rate times time equals distance, okay, 3, which is our rate, times our time would give us our distance. Okay? No surprise there. But if we draw a graph of the velocity, which is right here, it's given to us, the distance that object travels is equal to the area under the curve. Follow me. Yeah, I wish I could touch the blue. Okay, so here it goes. Velocity. Here's my constant, 3 feet per second. Okay, how many seconds did they go? 4 seconds. So isn't it 3 times 4? Yeah, so it's 3, this height from here to here, times 4, which is this distance from here to here. It's a rectangle, 3 by 4. Therefore, the area of that rectangle gives us the distance traveled. That's the area under the curve. Okay? Okay, simple connection. You don't have to memorize this stuff, but you'll be able to apply it easily using LRAM, RRAM, and because as we know, not everything is constant, hence calculus. Right? Curves, define that point right there. But what if the velocity is not constant? What if it's not constant? We might guess that the distance traveled is still equal to the area under the curve, but now it's not just a nice, neat little rectangle. So why don't we just draw nice, neat little rectangles and figure out their areas? No, not drawing little rectangles and adding them up, you stupid. Okay, so we have an example here where my velocity is 1/8 t squared plus 1. Okay, hence this nice picture here. Now, we could estimate the area under the curve by drawing rectangles touching at what corner, the left or right, is touching the line? The left. So they're left corners. And which RAM do you think we're going to use if the left corners are touching? The LRAM. This is called the left-hand rectangular approximation method. No, you don't get bonus points for saying it out instead of LRAM. Sorry. It's LRAM. That's what we're going to use. Now, what do I have to do? Yeah, I got to find the area of this rectangle, find the area of this rectangle, find the area of this rectangle, and add it all together, right? But in order to find the area, I need to know the dimensions of the rectangle, don't I? This is obviously 1, right? But what's this height? Well, that's given to us. It's 1. It looks like it's 1. But if it wasn't, how could I figure it out? If the chart wasn't there, if I had to fill in that chart. This is my x value, right? My y values go up. And how do I find the y value? Now, what do I plug in here? 0 or 1? 0.5, what do I plug in? Why do I plug in the 0? I need the left point. That's at 0. So when I plug in a 0 here, this goes away and I get 1. That's how that table gets filled in. Okay? Did you guys all follow that conversation that we just had? I know we have it, but did you guys all follow that?
Yes.
So I'm going to say 1 yes, so yes for the whole class?
Yes.
Okay, good. So, you know that this area is 1 times 1, which is 1. All right? Now this distance is also 1, but what's the height here? Well, I got to throw a 1 in now, because the height only goes to here, doesn't it? Where x is 1. So if I throw 1 in for my t squared, I get 1/8 plus 1, which is 1 1/8. There you go, right there. And we go ahead, so this is 1 1/8, which means based on our table, what do you think the area of this is? 1 1/2. Thank you very much. Because at 2, right? At 2, this left hand right here, that's the height, times 1. 1 1/2 times 1 is 1 1/2. What do you think the area of this rectangle is? 2 1/8. Because at 3, the left hand is the height of 2 1/8. So all I got to do is add all these areas together. These are my areas. If I add them all together, yeah, 5 3/4. If I add them all together, I get 5 3/4. Okay. I'm going to pause this now so you guys can really tell me how you feel. All right. We could also use a right-hand rectangular approximation method, which is RAM. So now each rectangle, the right-hand corner is coming to the line, not the left-hand corner anymore. So for this one right here, it's in the left-hand corner, it's now in the right-hand corner. So to get the area of this rectangle, guess what? I still use 1. If I look in the table that we just had, what is the value of this equation when t is 1? 1 1/8, right? So this is 1 1/8. Okay? Because I'm using the right now, the right side. So for this next rectangle, I want to use the right side, correct? That's right at 2. What's the value of this equation when t was 2? 1 1/2. Okay? What about this rectangle? That is the right side where t is 3. So what is that when t is 3?
2 1/8.
2 1/8. Look at it right here. I'm rewriting them, but they should be right there in your notes. Okay? And question. This rectangle right here, no longer, the last rectangle, no longer uses 3. It uses the right side. And when I put a 4 into my equation, it's 3 because it's 16 over 8, which is 2, plus 1, which is 3. So now I can add all those together. And what do I get? Well, an eighth and an eighth is a quarter, right? A 1/4 is 3/4. 3, 4, 5, 6, 7. 7 3/4. All right? Now let's take a look at this. What do you notice? What's that? What do you notice? What do you notice about the right hand approximation? Look at the graph and how we draw rectangles. And the left hand. Okay, so what do you think we can say then about the approximate areas that we're coming up with for the left versus the right? You can do what? Kind of. We're gonna get there. All right, I'll wait. Now, the middle. Oh. The MRAM. You're going to use the midpoint, which means I am not going to use my 0, which is my left. I'm not going to use my 1, which is my right. I'm going to use the middle, which is 0.5, right? That point. That's going to give me the area. So it is 1 by putting 0.5 in here, and they gave us that. So the area is 1.03125 using the midpoint. Okay? Now what is in between 1 and 2? 1.5. So when you use that point, and it gives you the area right here. 1.28125. What's in between 2 and 3? 2.5, right? And the area of that rectangle is 1.78125. What's in between 3 and 4? 3.5. And what's that area? 2.53125. So if I add up all those areas, if I add up all of, you can't do that quickly in your head, but it's fractions, guys, come on. That approximate area is 6.625. Now, this is our MRAM right here. What is our LRAM? What was that? And what was our RRAM? Yeah, I don't know why I put doing those. There you go. Way to recover. All right. So our LRAM seems lower. I mean, this seems to be more of a closer approximation than either the L or the RRAM. How come? Because you see this triangle right here that's cut off? That almost looks like you can fill in this space right here. So that's going to be real close. But when I do my L or my RRAM, this does not only the area that's under the curve, but gives you more, doesn't it? All this is extra. So chances are, this is going to be actually more than what the area under the curve is. Because we're calculating more area than what's under the curve. Our LRAM, we're missing all this area under the curve. So chances are, this is going to be actually lower than the actual area under the curve. So, we can kind of make a statement that if we're going to use LRAM, it's going to be lower than the actual area. If we use RRAM, it's going to be more than the actual area. And if we use MRAM, that's probably going to be our closest approximation to the point. Okay? So, I just want to bring one more thing up that's pretty important. In this example right here, the LRAM, the RRAM, and the MRAM, there are 4 subintervals. Our subintervals, what do you think those are? Yes. Okay? It's the number of subintervals. It's what you're breaking up the area into. There are 4 rectangles here. Okay, so there are 4 subintervals. That's what we're going to call it. Our 4 rectangles. As the number of subintervals increases, so does the accuracy. Because if I make these smaller rectangles, the gaps in between them of the triangles that aren't filled get smaller and smaller, don't they? Well, that's a big gap, but if I do something like this, that's just a small gap between what's above the line and below it. It's a major difference. Okay? So, keeping that in mind. The same thing with 8 subintervals. There are no longer 4, we just doubled it. Okay, there are 8. And look it, we are going to use, okay, this is 0.25. If these are 8 subintervals, this line falls right, where do you think this line falls at? What is this right here? 0.5. That's not the middle of an interval anymore. That's the beginning and end of an interval. So this would be 1.5. This would be 2.5. And this would be 3.5. So if I'm going to use the MRAM, which is our closest, what is the middle between 0 and 0.5? So this will be 0.25 right here, this height. What would be here? 0.75, which would be right here. And we get these areas all right here. They give us this stuff. Here's the area for each of our corresponding interval? I think so. So this right here would be 1.00781, and for the sake of time, that's why I have these written on the paper for you. I just want you to understand the concept. You'll have enough practice on your own. Here, all right, so I just add them up, but if I just add those up, look it. It's supposed to be closer to 6.625? We got 13.31248. Divided?
Well, wait.
Had to do what?
It's multiplied point t times b. And then add those up.
Okay, I see what you're saying. Close. Why am I going to take that and multiply that by 0.5? That's the width of my subinterval.
Oh my.
Each one of those 8 subintervals has a width of what? That's 0.5 from here to here. That's 0.5 from here to here. That's 0.5 from here to here. So I add them all up, and I multiply by the width of my subintervals. Okay? That should never change. Your subinterval is going to be the same for each rectangle. So the width is going to be the same for each rectangle. So why didn't we do that for the first 3 problems we did?
Because there's 1.
Because the subinterval is 1. 1 times anything is itself. Yahtzee! Okay, so sometimes what people like to do is they get all these, they actually, instead of multiplying the sum by this, they distribute it into each one of these, then add, which I think is a lot of work. But sometimes if you see that in a book, you should know that, oh, well, instead of just adding it and then multiply, they distribute it to each one, then add. And guess what? Guess what the approximate area is if we do it this way with more subintervals? We add them all, well, it's right here. 6.65624. I want to know what the exact area is.
Sure.
6.6 with a line over it. So 6.66. That is a lot closer than our MRAM with 4 subintervals. Okay? It's a lot closer than our LRAM and RRAM with 4 subintervals. The more subintervals you get, the more accurate you'll get to here. So what happens if there's an infinite amount of subintervals? Don't worry about that.
Oh, see, that's
Yeah. Don't worry about it, guys. I still love each and every one of you. So, based on what we kind of discovered on the drawings, if I'm using the LRAM, what is that going to be compared to the real area? Less. L is for left and less. If you take the LRAM, you should know that, okay, this is an approximation area, but it's probably a little bit less than the real area. What is a real-life situation where you might want to underestimate what you're actually going to have to use? Right? You want to make sure you have enough money. That's going to be RRAM. You want to make sure you have more than enough money to cover your costs. Let's say, this is a really crazy example, but let's say water becomes really precious, which it will eventually one day. And you have a pool, and you want to fill it up. And they charge you per gallon like an outrageous amount. What do you want to make sure? Oh, yeah, what am I going to do? Let it overflow the pool. No, you want to make sure you have just under what you need to fill your whole pool, don't you? You do. Okay, and that's just a silly example. But RRAM, obviously, money. You want to make sure you have enough to cover your costs for your business. You're going to supply a service to somebody. You're going to buy materials. Oh, I can't build your deck. I didn't have enough money to buy it. Oh, then why am I going to pay you? Now you're out. Okay? And obviously, MRAM, that's closest to your true area. RRAM is more. MRAM is closest. And the more subintervals or intervals, the more accurate it will be for any one of those. Now, your notation, MRAM sub 10. That's not a minus sign, that just means, I should have probably put an arrow there. It just means there's 10 slices of subintervals. Okay? So if I were to put an 8, I would have had to put an 8 there for the last problem we did, because there were 8 subintervals. Okay? Maybe we'll get there. Do you remember when we learned derivatives and we had to do the difference quotient?
Oh,
F of x minus h, f of x plus h minus f of x all over h, and I had you do that several times before I should do it. when we do integrals, we're going to be able to find this real easy. Okay? All right. Why don't you guys do a problem on your own, and then we'll go over it. Okay? Okay, so we went ahead and did the LRAM and RRAM without recording. But if you did your LRAM correctly, it is 6.875 right here. If you did your RRAM correctly, which most of you guys did, you get 11.375. Now the MRAM. Okay? Now, you need to figure out what is the middle for each one of those intervals, and that's going to be your t value that you square. So, if I have my t and my vt, well, what's the middle right here? 0.25. What happens when I square 0.25? 0.0625 when I square 0.25. Because don't forget, we're squaring everything. Okay. What's the middle here?
0.75.
What do you get when I square 0.75? 0.5625. That first one's correct. It's 0.0. Yes, it is. Whatever. What about here? 1.25. What happens when I square that? Thank you. What is here? 1.75. What happens when I square that?
3.0625.
Wait for it. Here is 2.25. What happens when I square 2.25?
5.6.
Wait, 5.1. Come on.
25.
And what's the last one here?
7.5.
Okay, so if I take 2.75 and I square it, I get what?
7.5625.
So I need to add all these up and then multiply it by what? 0.25 is the middle. But I multiply my sum by the width. Which is 0.5, the whole width. The width always. Okay? My sub-interval length, I guess, is 0.5. So I got to add those all up, then multiply it by 1/2 or 0.5. If you do that correctly,
You get 1.9375.
Yahtzee.
So no matter how small the interval is,
That's what you're multiplying your sum by. We didn't do that initially because the LRAM and the sub-interval was 1. We didn't have to do that. So, okay? So you got some homework to practice this stuff, guys, okay? Yeah.